All right, welcome back, class. Let's continue our discussion on control charts. And today we'll talk about another type of a control chart called X bar and S control chart. Previously, we have talked about X bar and R control chart. But before we talk about that, let's talk about the differences between range and standard deviation, because truly, earlier we were doing a range-based monitoring of process standard deviation, and now we'll use standard deviation itself. So let's see why it makes sense to use range as opposed to just using standard deviation. And in fact, when standard deviation could be useful for monitoring the variability. So the first factor is sample size. If your sample size is small, it's just is easier to compute range. And so you would want to prefer range when the sample size is small, preferably. Now, when the sample size is large, this is where you would want to use standard deviation. This is standard deviation preferable. And let me give you an example for this, why it is more preferred to use standard deviation when the sample size is large. Now imagine a classroom of, containing PhD students. Most of these PhD students would lie between the age of, somewhere between 20 to 30 in most cases. But it happens once in a while that you might see an outlier. And this was for my case, because when I was doing my PhD, I still remember there was a student who was 65 years old. So now, if you look at this data, you have a bunch of students in this range, 20 to 30, but then you have a single outlier here. If you compute the range of this entire data, it's roughly about 45. But majority of the data is just lying in this range of 10. So what we're basically trying to see here is that range is highly sensitive to outliers. In contrast, if you compute standard deviation from the data, standard deviation is a little bit robust or more robust as compared to range to outliers. So I would say standard deviation is robust to outliers. And that's when standard deviation is more preferred as compared to range. And then there's another instance where your sample size is actually variable. And if your sample size is variable, you would again want to use standard deviation to monitor variability. All right, so now we'll turn on to X bar and S control chart. Again, we start with known mu and known sigma. So when we talk about X bar control chart, it mostly remains same as what we have talked about. UCL is mu plus A sigma, CL is mu, and LCL is mu minus A sigma. Let's look at where A is. Let me write this down. 3 divided by square root of n. Let's talk about, for the first time, an S control chart, or a sample standard deviation control chart. S control chart. Remember, in order to construct a control chart, we need its mean and we need its standard deviation. Now again, just like range, some of these results already exist for us. We don't have to derive them, we can just use them. Mu of S is sigma times C4, and sigma of S is sigma square root of 1 minus C4 squared, where C4 is a constant. Again, this constant is available in the appendix of constants. Okay, so now let's construct our UCL. UCL is equal to sigma times C4 plus 3 sigma square root of 1 minus C4 squared. You can take a few things inside the constant. Inside parentheses, C4 plus 3 square root of 1 minus C4 squared. And then this becomes sigma times B6. This constant inside the parentheses is B6. Central line is simply sigma times C4, and then your LCL is sigma times C4 minus 3 sigma square root of 1 minus C4 squared. This is equal to sigma times C4 minus 3 square root of 1 minus C4 squared. This is equal to sigma times B5. And then that gives you an S chart. So this is your S chart. Right, and now again, just like what we previously did, if sigma and mu are unknown, we have to estimate them from data. And so we'll do the same thing again, one more time here. We will compute them from the data. So your data looks something like this. Again, you have sample. Your sample goes from 1 to dot 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 up to m. You have observations from 1 to dot 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 up to n. And for every single sample, you're going to compute x bar. So you get x1 bar, x2 bar, dot 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 up to xm bar. And then you have sample standard deviation for every sample, which is S1, S2, dot 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 up to Sm. And we know Si, right? Si is equal to 1 over n minus 1 xi minus xi, actually it's xij minus xi bar x, sorry, I'm having some trouble here writing this down. It's xi bar summation. Actually, let me clear it up a little. Summation of j is equal to 1 to n divided by n minus 1 square root of this and then square root of this. And that gives you sample standard deviation for the ith sample. And we can also compute the grand average, which is x double bar 1 over m summation of xi bar, I is equal to 1 to m. And we can compute S bar, which is 1 over m summation of Si, I is equal to 1 to m. Now, well, we have estimate of X double bar and S bar. Let's look at the X bar and S control chart, assuming that mean and standard deviation are unknown. There are some redundant slides. I'm going to take this off. Actually, this should go into unknown mu and sigma. So I'm going to move it to a subsequent slide. Yeah, this would go right here. And then these are some redundant slides, so I'm going to cancel them out. All right, perfect. So now we have an estimate of X double bar and S bar. Let's start by defining our X bar control chart. So X bar control chart. Again, we need mu of X bar, which is mu, and sigma of X bar, which is sigma. So we'll estimate mu with X double bar. So mu hat is equal to X double bar, which implies mu of X bar hat. This is X double bar. Similarly, we will estimate sigma with S bar, which we have computed from data, S bar divided by C4, which gives us sigma hat is equal to X bar divided by C4, which implies sigma of X bar hat, this is S bar divided by C4. Oh, sorry, I think I'm missing here a square root of n. So I'm missing a square root of n here also. All right, so now we have mu of X bar hat and sigma of X bar hat. Let's go ahead and compute our control charts. So first you will have your UCL equals to, let me take a look at this, x double bar plus 3 s bar divided by c4 times square root of n. Center line is just x double bar, and LCL, this is x double bar minus 3s bar divided by c4 times square root of n. Again, we can make some simplifications here. We can write this as x double bar plus a3 times s bar. Center line remains as is, and lower control limit goes x double bar minus a3 times s bar, where a3 is equal to 3 divided by c4, 3 divided by c4 square root of n. That's your a3. Okay, and so this becomes your x bar control chart with unknown mu and sigma. So we have done x bar control charts. Let's finish up S control chart, and then we should be done with more or less all of the control charts, major control charts. For S control chart, we need mu of S, which is equal to sigma times C4, and sigma of S, which is sigma times square root of 1 minus C4 squared. We estimate sigma using S bar over C4. So now I have sigma hat equals to S bar over C4. So I can say mu of S bar hat, this is S bar, C4 gets cancelled, and sigma S hat, this is equal to sigma times 1 minus C4 squared divided by C4. And now we have everything in place. We write down UCL equals to S bar, sorry, sigma S hat, I made a mistake here. This has to be S bar times square root of 1 minus C4 squared divided by C4. This your UCL is S bar plus 3 S bar square root of 1 minus C4 squared divided by C4. CL is S bar, and LCL is S bar minus 3 S bar square root of 1 minus C4 squared divided by C4. Again, you can take out S bar common, and then you get S bar times 1 minus 3 divided by C4 square root of 1 minus C4 squared. The term inside the parenthesis here is B4, so we get S bar times B4. Center line remains same, lower control limit becomes S bar 1 minus 3 divided by C4, 1 minus C4 square. This is S bar times B3. And that, my friend, is the end of control charts, major control charts, not all the control charts, because again, this course is control chart, S control chart. Now, what I've done here is, if you scroll all the way down to the selection notes, you'll see that I have nicely summarized all of these control charts formulas in one little table, which you can use easily when you are doing assignments or even an exam. You can actually make a printout of this and then just simply follow this. What this basically, I'll try to walk you through this. So the first row is basically the assumption that mu and sigma are known. Right? So if the mu and sigma are given to you, you can construct X bar and R chart, or you can construct an X bar and S chart. Now, once mu 0 and sigma 0 are not given to you, you'll start by X bar and R chart and estimate some values from data, which is mu hat and sigma hat. And then you can construct X bar and R chart, which is your second row. And then the last row is X bar and S chart, which is when you estimate mu hat and sigma hat again, and then you can get the X bar and S chart. All right, now let's go back and do a couple of problems based on what we have just done. So this question is asking you to construct and interpret an X bar and S chart using the piston ring inside diameter measurements. So you have about 25 measurements, 25 samples in this table. For every sample, you have 5 observations. And then we're asked to construct an X bar control chart and an S chart. So let's look at this. Your X bar control chart is written as UCL is equal to X double bar plus A3 times S bar. And X double bar and S bar, you can see on the top right corner, you have these numbers given to you. If you plug them in, and if you compute A3, if you estimate A3 from the table, you'll get 74.014. Center line is just X double bar, which is 74.001. And LCL, this is X double bar minus A3 times S bar, which is 73.988. And now we can also compute our S chart. For S chart UCL, this is equal to B4 times S bar, which is equal to 2.089 times S bar, which is given in your table as 0.0094. That gives us 0.0196. Center line is 0.0094, and then LCL is equal to B3 is just 0, so your LCL is 0, and that gives you the X bar control chart and S control chart. Now, there's a quick variation of this problem. Sometimes you actually see that you'll have missing data. For instance, in this table, for sample 2, you have missing data. For sample 6 and 7, again, you have missing data. And this missing data actually leads to a variable sample size problem, right? Because every single sample has a slightly different sample size. So what we do is we just change the way we compute X double bar and S bar. Everything else remains same. We just change how X double bar and S bar looks like, because now it depends on the sample. So what we can do here is we can compute a weighted sample average and a weighted sample standard deviation. So what we do here is for every sample, you calculate Xi bar, which is equal to 1 over Ni. Now, instead of using N, I'm using Ni to indicate the sample size of that particular sample. Summation of Xij, j is equal to 1 to Ni. And from here, I can compute X double bar is equal to summation of Ni times Xi bar. I is equal to 1 to M divided by summation of Ni, I is equal to 1 to M. Similarly, we'll compute Si equal to Xij minus Xi bar whole square, summation of j is equal to 1 to Ni divided by Ni minus 1 square root. That gives you Si, and then you compute S bar equals to square root of Ni minus 1 times Si square, summation of I is equal to 1 to M divided by summation of Ni, I is equal to 1 to M minus M. That's a little bit of a complicated formula. So what I'm going to do here is I'm going to quickly show you how to compute a couple of values of X double bar and S bar in this example. So in this example, let's start by X double bar. X double bar is simply, for every sample, we already have computed xi bar. So you'll start with the first sample, which has 5 observations. So n1 is 5, so 5 times 74.010 plus sample 2 has 3 observations, so it is 3 times 73.996 plus dot 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 up to the last sample, which has 5 observations, 5 times 73.998, and then you divide this with 5 plus 3 plus dot 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 up to 5. And for this problem, it will give you 74.001. Let's also look at how we can compute the weighted sample standard deviation. Weighted sample standard deviation S bar, this is equal to square root of, it's a big square root, it's n minus 1. So for the first sample, we have ni is 5, so it's 5 minus 1 times si squared. Si is 0.0148, 0.0148 squared, plus for the second sample, we have 3 observations, so 3 minus 1 times 70, sorry, not 70, times 0.0046 squared plus dot dot dot. The last sample has 5 minus 1 times 0.0162 whole squared and divided by 5 plus 3s plus dot 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 up to 5 minus m, which is 25. And then this gives you 0.0103. Now your control chart remains more or less same, but what you have to keep in mind is even when you write down your control chart, your constants actually depend on the sample size. So let me show you what I'm trying to say here. So let's say when I'm trying to construct my upper control limit and lower control limit for, let's say, X bar and S control chart, let's start with sample 1. Here, N1 is equal to 5. So your UCL, this is X double bar plus A3 times S bar. We already have X double bar and S bar, but A3 depends on N. N is 5. So in this case, you will have 74.001 plus 5 times 0.0103, which is 74.0157. But for sample 2, your N2 is only 3. So your UCL will change because now A3 will change. In this case, your UCL is 74.001 times, plus, I think I made a mistake here. It's not 5. I think I made a slight mistake here. So let me fix that. 74 plus 001. A3 for n equals to 5 is 1.427 times 0.0103. Now A3 for n equals to 3 is 1.954 times 0.0103, which leads to 74.021. Right? Similarly, when you compute the LCLs, and you can continue doing like this. Now let's look at LCL. So sample 1, N1 equals to 5. Your LCL turns out to be 73 point. I'm just giving you the final numbers. Instead of plus, you have minus sample 2, and 2 equals to 3, which implies LCL equals to 73.981. So you see, for every single sample, if the sample size is different, then your UCL and LCLs are going to be different, right? And in fact, when you construct your control chart, your control chart might look a little bit funny. You still have your center line at X double bar, which in this case is 74.001. But for every single sample, your upper control limit might be a little bit different. Not for everyone, but most of them. Whenever the sample size is different, it will be different. So this is how your UCL will look like. This is how your LCL look like. It's symmetric, so I'm trying to be symmetric here. That's how your UCL and LCL will turn out. Now I do have, when I do this practice on jump, I will actually walk you through this. So you will get to see how these control charts really look like. All right, now let's look at the final most control chart of this case, of this chapter, which is really just a special case of what we have seen before. When sample size n equals 2 becomes n becomes 1, there is a problem. Let's say your sample 1, 2, 3, dot, 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 up to m. For every single sample, you only have one observation. So you have xi, you have x1, x2, x3, up to xm. You can compute x bar, so you'll get just those numbers, x1, x2, x3, up to xm. But here's the problem. Your range is going to be 0, 0, 0, 0 to 0. And your standard deviation, well, you cannot compute standard deviation, because for standard deviation, you have to divide by n minus 1. N is 1, so that gives you 0. So you really can't use traditional control charts. And this is where, when n equals to 1, we use something called moving range. Moving range is defined as, moving range is equal to xi minus xi minus 1 absolute value. That's what moving range really means. So let's say for every index 1, 2, 3, up to m, you have observations xi, let's say x1, x2, x3. My 3 is not good, so let me do it again. x3 up to xm. And now we can compute moving range, which is mr. For the first sample, there's no moving range. For the second sample, it is absolute value of x2 minus x1. For the third sample, it is x3 minus x2 absolute value, all the way up to xm minus xm minus 1 absolute value. And now I can compute mr bar equals to mr1 plus mr2 plus dot 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 up to mr m. Now, we don't have mr1, we start with mr2. So I'm going to take this off here, okay? And then I'm going to divide this with m minus 1, because we only have m minus 1 moving ranges. And then we use moving range for estimating, or you can also say monitoring variability. It's like a substitute for sample standard deviation or range. And then you have your usual x bar, which is 1 over m, summation of xi, I is equal to 1 to m. All right, now we can construct something called an individual x chart and moving range chart. Your individual x chart is UCL equals to x bar plus z alpha over 2 mr bar divided by d2. CL is just x bar and LCL is x bar minus Z alpha over 2 MR bar divided by D2. Your moving range chart, your UCL is equal to MR bar plus Z alpha over 2 MR bar D3 divided by D2. Center line is MR bar, and then LCL is equal to MR bar minus Z alpha over 2 MR bar D3 divided by D2. Now, one thing that you have to keep in mind is you have these constants D2 and D3. If you scroll all the way back to appendix number 6, you will see that these values are not defined, or they don't exist for n equals to 1. So if you look at this table, you have your D2s and then D3s right here, but you don't have any row for n equals to 1. You can pause the video here and take a look at it. So since you don't have these values for n equals to 1, we actually use a substitute from n equals to 2, right? So you'll basically use this value and this value of D2 and D3, okay? So let me make that comment here as well, so you don't forget. My comment here is use D2 and D3 corresponding to n equals to 2 as a substitute. All right, that's pretty much ends our discussion on control chart. That was the last control chart of chapter number 5, control chart for variables. I do have, again, we have talked about this summary slide here. We have talked about phase 1 and phase 2 monitoring. And I do want to talk about an example problem here that basically uses XBAR control charts. So let me try and bring that example here in a little bit, and then we'll try to solve that problem. And that is, again, an important problem. As a quality control engineer, you should be able to, be able to solve these type of examples. And then this is the example right here. So in this problem, it gives you an XBAR and R control chart n equals to 4. It says construct the corresponding XBAR and S chart. Okay, so if I have to construct XBAR and S chart, let's try to write this down. XBAR chart looks like UCL is equal to X double bar plus A3 times S bar. CL is X double bar. LCL is X double bar minus A3 times S bar. That's your X bar chart. And then S chart is UCL equals to B4 times S bar. CL is S bar and LCL is B3 times S bar. In this scenario, you need two things. You need X double bar and S bar to construct your X bar and S chart. You probably already have X double bar from this previous X bar chart. From previous X bar chart, the center line gives you X double bar equals to 620. But you still need S bar. And to estimate S bar, this is the trick that we're going to use. From R bar chart, you have R bar equals to 8.236. And if you go a little bit earlier into our discussions, we used a formula. We used an estimate of sigma using R bar divided by D2. So if I plug in here R bar, we already know n equals to 4. So we know D2. I can say that sigma hat is 8.236 divided by 2.059, which is 4. And now if I have sigma hat, I also know that sigma hat can be estimated using S bar divided by C4, which means I can estimate S bar equals to sigma hat times C4, which gives us, again, C4 is available from the table. This gives you 3.865. And that's what exactly we needed. right? So now you can plug these numbers in and you'll get X bar chart UCL 626.29. Center line is again remains same 620. LCL is 613.71. And then on the right hand side, your S chart, your UCL is 8.351, S bar is 3.865, and LCL is 0 because B3 is 0. Right? Okay, there's one more problem. It says, suppose the process mean shifts to 610. The current process mean is 620. What is the probability of detecting the shift by at least a third sample after the shift? Right? And let's say we don't want to make any assumptions about whether the process is, all right, let's not make any assumption about the value of Z alpha over 2. That's what I'm trying to say. Actually, let's do it. Let's do it the other way around. Let's actually do both. Let's first assume Z alpha over 2 equals to 3, and then next let's do not assume about it, right? And let's see what are the differences. So the question says, suppose the process mean shifts to 610. What is the probability of detecting the shift by at least a third sample after the shift? So the question is asking probability of detecting the shift by at least the third sample after the shift, given the process is out of control. Okay, now I can say that if the shift has to be detected by at least the third sample, that means shift could be detected by the first sample or by the second sample or by the third sample, right? Instead of using all of these different scenarios, I'm just going to say this is equal to 1 minus probability not detecting shift by the third sample. This makes it easier because now I can say if the shift is not detected by the third sample, then it was not detected by the first one, not detected by the second one, and also not detected by the third sample. So I can say 1 minus probability not detected by the first sample given OOC times not detected by the second sample times not detected by the third sample. All of these three events are exactly same. They're identical. So I'm going to say raised to the power 3. So now I have this is equal to 1 minus probability X bar. So not detecting the shift means that your sample observation is still inside the control limits. So this is less than equal to UCL greater than equal to LCL given OOC raised to the power 3. Now here, there are two assumptions that we can make. This is definitely beta type 2 error, right? So you can potentially write this as 1 minus beta cube. And if you know Z alpha over 2, you can compute beta. If you don't know Z alpha over 2, you will just plug in UCL, LCL, and then you compute the probability. So let's say in the first scenario, let's say we don't know, we don't assume Z alpha over 2 equals to 3. So in this case, what we will do here is we'll just simply do 1 minus probability X bar less than equal to UCL is 626 greater than equal to 614 given the process is out of control. Now, what you have to keep in mind is we need to know the distribution of X bar. So X bar follows normal distribution with some mean and some variance. And this is very, very critical. The process is out of control. the true process mean was the central line, which is 620. But since the process mean has shifted to 610, now your mean is 610 and your standard deviation is sigma, which is 4 divided by square root of n, which is 4. This is equal to 2. And now you can do this on your calculator. You can do norm CDF, lower limit 614, upper limit 626, comma mean 610, and standard deviation is 2. And if you plug this into a calculator, you will get the second term is, this is equal to 1 minus 0.023 raised to the power 3. And this is what you can get from your calculator. So see if you can compute this, and then we just do minus 1, which gives you something very close to 1, right? Which is 0.99987, something like this. Now, we did not make any assumptions about z alpha over 2, but let's say for the time being, if let's say, if z alpha over 2 is 3, which you can actually even compute by looking at UCL and LCL. You might not even have to guess many a times. You can just compute that from the data. And in this case, I actually know it's a 3 sigma control limit. So if you assume z alpha over 2 equals to 3, your beta is phi of z alpha over 2, which is 3 minus delta. Delta is 10. It goes from 620 to 610. So delta is 10. Square root of n is 4 divided by sigma, which in this case is also 4, minus phi of -3, -10 times 2 divided by 4. So this is 5. Now let me see if I can get this on a calculator and quickly compute this value. So you have phi of 3 minus 5 negative phi -8, and this is approximately equal to 0.0228, which is very much similar to what we computed there, which is 0.023. Again, if you plug this in, you should be able to compute the desired probability. So I really wanted to show you that you can use either of these two methods. Most of the problems I will tell you what is the value of z alpha over 2, and many times I'll specifically tell you that do not assume z alpha over 2 equals to 3, right? And depending on the scenario, you can compute these probabilities. Right, so that's the end of chapter number 5. We'll see you later on chapter number 6. Thank you.